Today we shall discuss about the timers with counters. Basically, to extend the range of timers, this particular phenomena or this particular concept is used, right, to extend the range of the timers. Let us try to see how exactly we will be able to materialize this. Let me take up one example here. Now, I will start by drawing the ladder diagram here with our Mitsubishi configuration only. Now you can see here, I start with the power rails here. Let me start with one input switch here, followed by a normally closed timer switch. I will tell you what for this is used. Now I will have a timer here. Please note that I am drawing a timer here, not the counter. Then here I would bring in the counter. As usual, your counter will be having three parts. One is reset, and another is the count value. Again, I will take it as C450 as usual. There is some problem with this pen. Wait. C450, and this C450, let me have K of 24. I will tell you why I am having K of 24 here. Then the next one will be as usual out here. This is, one second, there is some problem here with this. Okay, reset. I am using a counter with the nomenclature as C450 and K equal to 24 and out. So now you can see here I am using one more rung here, that is to reset your counter. Let me use one more input here, and here this timer let me take this as T450 with K. Here I will take K of say 3600. K of 3600. This is very important now. This is again T450 contact only. This is T450, and let me have here this as X400 T450, that is the timer with K equal to 3600. Then now I would like to have an output here. This is Y430. Let me take it as Y430 only, and this is my 450 contact. So here let me take this as X401 or something like that. So this X401 is not really a part which participates in the action of the timer with counter, right? As I have already told you here, you have the timer range extended by making use of the counter. So probably you may come across some examples which you have taken in your microprocessors or microcontrollers. Suppose if you load a count equal to FF, okay, so FF is nothing but 255. So depending upon the instruction cycle and all, for a maximum count you may have a maximum time delay possible. Let us say that 2 seconds, one example, okay, with a count of FF you get a delay of 2 seconds. If you want more delay than 2 seconds, then with that particular count it is not possible for you to realize that delay. So what would you do is, you will use a loop inside the loop technique, right? You will have an external loop, you will have this as the internal loop, right? So suppose if you want the loop to give you the entire program to give you 10-second delay, whereas your loop is giving you only 2 seconds delay, what you would do is you would repeat it 5 times from an external count or something like that. You take an external count which is initialized to 5, then you get a 2-second delay, then make it 4, then again you get a 2-second delay. I think you can quickly recall these things since you have already studied either microprocessor or microcontroller. This is what is the logic that is generally used. So a similar technique here is used to extend the range of the timers. Now let me say that I have k equal to 3600 for the timer T450. So T450 is my timer, and I will have maximum 3600 seconds which I can get it from this particular timer. So 3600 seconds, that means that it is 1 hour. The total delay here I am going to get it as 1 hour. Now if at all I want to have the counting for one full day, I have to have the counting for one full day, which I must multiply it by 24, right? So with the limitation of this, it is not possible for me to have a 24-hour count. So therefore what I would do is, I every time initiate or start the timer which counts for 1 hour, as you can see here, 1 hour. Then I will have an external count here, either it is starting from 1 or 24, whatever it is, depending upon whether it is a up counter or down counter, right? Once the timer gives me the output, what I would do is, I will increment it. This becomes 1 plus 1, and again I will reset the timer and I will make it to count for another 1 hour. Again I will increment it, I will make it to count for another 1 hour. Like this, if I make it to count it for 24 hours or 24 times, I would get a total delay of 24 hours. So this is how I should be able to get my task completed by virtue of the combination of the timer and the counter. So the same thing is represented here also, this diagram. You can see here how exactly it is materialized. So you have one input X400, which is to turn on your timer or turn on your action of the timer, right? And since K is for 3600 seconds, the timer will give you the output at after a delay of 1 hour. So therefore I must have that timer contacts coming here. This is T450 here. This is T450. So you have reset the counter with the value of k equal to 24, as you can see here, k equal to 24. So now this timer, what it would do is it will start the counter for the incremental value of 24, right? So every time the counter every time the timer resets, so this particular switch, which is a normally closed switch, this will take care of resetting the timer as well as reinitiating the timer. That means once you have 1 hour delay, right, upon the increment of the counter, so what happens is this timer resets and it will start counting again. So that would give the second pulse here. After the first 1 hour, you would get one increment here, that is T450, which is getting connected to out here, that is something like this, one pulse. Then after the second hour, you would get the second pulse. After the third hour, you would get third pulse. Like that, when you have total 24 pulses generated, which accounts for the delay of 1 day, finally the counter contacts, that is C450, right? So it will activate to generate the output, right? So that means ultimately after 1 day, after a delay of 1 day, your output should be activated, right? So the output is activated after 1 day. Before that, because of the time limitation of your timer, right? So you would have the delay of 1 hour each, which is going to activate your counter at the end, and that will make your output to be activated. This is how, so now this is important for us, because every time upon the increment of the counter from 1, 2, 3 and all, so your timer should reset and it should start recalculating. It should start recalculating from the beginning till 1 hour time delay is completed, that is 3600. So this is one example where it is possible for you to have the extension of the range of the timer, if at all the required time delay is not possible by virtue of the very basic range of the timer. You can use the counter to extend the time delay. Okay, so this is one example which indicates that. Let us look into one more simple example of the similar kind, so that you become accustomed to this. Devise or design a ladder logic. Design a ladder logic using normal counters, and timers to measure 50 days. To measure 50 days. Design a ladder logic using normal counters and timers to measure 50 days. So this is what is the problem statement, and this problem is also on the very similar grounds what we have discussed in the previous case. Now here some assumptions are to be made here. The basic assumption is that the scale or the time scale is equals to 1. The basic time scale is equals to 1. This we have already seen while we discussed about the timer operation, right? So now again in this case also we can take k equal to 3600. K equal to 3600. That means when my time scale is equal to 1, k 3600 means it will give me a delay of 1 hour. It will give me a delay of 1 hour. Time scale equal to 1, k equal to 3600, which gives me a delay of 1 hour. Now I will have to measure 50 days. So my k in this case is 3600, as I have already written there for timer. K equal to 3600 for timer. Now I will have to do it for 50 days. Earlier I had done it for 1 day. So I had multiplied this by 24 as long as the counter is concerned. Now since it is 50 days, I have to multiply it by 24 into 50. That is, for counter, k value is 24 into 50, that is 1200. This is the only change what you have from your previous diagram. So otherwise all other things look very alike here. So with this background, we should be in a position to now draw the ladder diagram for this. Let me draw the power rails here. So again, let me start with one start switch, followed by the close contact of your the timer, because every time it has to be reset. Then comes the actual timer here. Then you may have one more. I will first draw the counter here. So this is reset, this is the counter, and this is output. This will be like this, and this is for resetting the counter. Then finally I would have the output. This is my output. So now I need to, this I would write as X 400, then this is T, I would take it as T 450. This I would take as T 450. And again here also I would have T 450 with K of 3600. T 450 with K of 3600. Here I would have reset. this is reset, and this is my one second, C450. This is my counter with K of 1200. K of 1200 out. Now here you can have one more, X401 or something like that. That is this is X401, and every time if you want to increment the counter, you know that you should have, this is T450, this is T450, and here you have C450, and here you have, let us say, Y430 or something like that. This is how you should be able to draw the ladder diagram. You can even write the instructions here for this particular ladder diagram. So please try writing the instructions. We can write it here. The first instruction happens to be LD X400, as you know. Then the second instruction ANI, right? ANI T450, ANI T450. Then you have out T450 with K of 3600, LD X400 and inverted, that is the normally closed switch, ANI T450, out T450, then K 3600. Then the next instruction is LD X401, LD X401 followed by RST, that is counter 450, RST C450. Then the next instruction is LD T450. You can see in your earlier program example also, LD T450, not C, T450. Then out C450 and K1200, K1200 followed by LD C450, then out Y430. Here what you need to do is you have to mention what exactly we mean by Y430, because the end of the counting of 50 days is indicated by Y430. That is very important point to be noted, right? The end of counting of 50 days is indicated by an output Y430. The end of counting of 50 days is indicated by an output Y430, and also an input X401 is used to reset the counter. An input X401 is used to reset the counter. And one more instruction also you can write. The process of counting 50 days is initiated by an input X400, because these are all the assumptions which you have made here, and those assumptions are to be mentioned somewhere, right? So this is a program wherein you should be able to get a count of 50 days by making use of the timer and the counter, which goes in the similar way what we have done in the previous program. Now let us look into one more example on these things. Please note down this example statement or problem statement. Develop a ladder diagram that will latch an output 20 seconds after an input has been turned on. 20 seconds after an input has been turned on. The timer will continue to cycle up. For 20 seconds and reset itself until input is turned off. After the third time, the timer has timed to 20 seconds. After the third time, the timer has timed to 20 seconds. The output the output will be unlatched. The output will be unlatched. Please try to go through the problem statement here carefully. Develop a ladder diagram that will latch an output 20 seconds after the input has been turned on. So this is a clear case of using a timer followed by an input switch. All of you are very well aware of it. And the next part of the statement is something like this. The timer will continue to cycle up 20 seconds, cycle up for 20 seconds and reset itself until the input is turned off. Until the input is turned off. After the third time, please see this statement carefully. After the third time, the timer has timed up to 20 seconds. That means every time the timer will time up for 20 seconds, and after timing up for 20 seconds, it will reset until the input is turned off. It will reset, right? So now if you want to set it again, you will have to again turn on the input. So this will happen 3 times. After the third time, the timer has timed up to 20 seconds. The output will be unlatched. The output will be unlatched. That means, how do you interpret this particular situation here in terms of your timing diagram or something like that? So now, let us say you have one input signal here. Okay. So once your input signal is present there, will start and it will count up to 20 seconds. This is a 20-second period. And what the problem statement tells is the timer will continue to cycle up for 20 seconds and reset itself until the input is turned off. It will remain like this. Now your input may be of this kind. Okay, it will remain reset. Now until the turned off. So somewhere here I have turned off the input. Okay. So now again I will latch the input. I will make the input to go high, and again your timer will go high here. Okay. So this timer will again for say 20 seconds. Let us say that here I have again turned off and turned on the input, something like this. Then this will be the third count now for the timer. Now is turned on or turned off here onwards, it doesn't matter. So this is the 20-second period. This is the second 20-second period. This is the third 20-second period, as long as this is concerned. So this is the input. Here you have got the input. So now after third 20-second period, after the third time the timer has time to 20 seconds, the output will be unlatched. So that means in the beginning, the moment you have the timer on, the output is latched here. So let us say that this is the output. The output will turn on. Okay. So devise a ladder diagram that will latch 20 seconds after an input has been turned on. So that means your output would latch somewhere here, not here. So the output is zero only here, here. Your output will become high somewhere here, because your problem state tells that this is the output. Develop a ladder diagram that will latch an output 20 seconds the input is turned on. The input is turned on here. Simultaneously your timer is also turned on, and this period is 20 seconds. So now your output is turned on here. So the timer is turned on for the first time. Again the output will remain high. The timer is again turned on for the second time depending upon the input. Again the time remain high only up to here. The timer is turned on for the third time, and now it is here. Here your output is required to be unlatched. So you get output signal like this, and it is not possible for us to understand what is the time period here. The total time period here is no, because we will not be knowing what exactly is the time period here and here. We know only the time period here, which is the 20 second, and which is minimum there will be 40 seconds minimum, depending upon where exactly you latch the input, or where exactly you turn on the input. Okay, so this is the problem statement, and accordingly you will have the timing diagram for this particular problem statement. Now I will rub these things off, that is the timing diagrams, and you should be able to draw the ladder diagram for this particular case. So let me wipe off these things so that I draw the ladder diagram. Now let us start drawing let me have the power rails like this. So my input as usual happens to be the first one, and whenever I use the timer bar counter, so needless to mention that your timer contacts with a normally closed contact would appear in the first rung itself, so that every time the counter increments, the timer resets itself and starts counting again, or starts making the required delay again. So now I would have one more timer. One is for this and one is for the counting of the next 20 seconds. So I would have the switch here, and this switch would make me to connect to one more timer here. So the first timer I will write it here. So now this is my